Hi, welcome to 7.3. We're talking about volume again, but this time we're going to talk about a different technique. It's called the shell method. We did the disc and washer. This is the shell method. So if you remember how we did the disc and washer, what it was is like finding the area of the circle that was generated going across the axis or going up, right? This time we're going a little bit differently. Now think about the cylinder. Now this cylinder has a hole in it. Now if P and is our radius here. This outer edge is P plus W over 2, where W is the width of this ring, and P minus W over 2 is this part down here, is this distance. So P is the distance from the axis to the center of this region, the cylinder. The radius of the inner cylinder is P minus W over 2, radius of the outer cylinder P plus W over 2. So our volume is going to be the volume of the cylinder minus the volume of the hole. That volume of the cylinder is P plus pi over 2 squared, and I think this is supposed to be I'll leave it like that for now. I think this is a W is supposed to be a pi. I think it didn't come out right. Times H, so you have pi r squared H, that's the volume of the cylinder, minus pi r squared H. This is the inner radius, P minus pi over 2. Yes, this is supposed to be a W here. This is a mistake. That's a W. I apologize. So this works out to be 2 pi times P times H times W, which is 2 pi times the average radius times the height times the thickness. So let me scroll this up and let's put this together. Now this formula can be used to find the formula for the volume of a solid of revolution, so solid of revolution like we've been talking about, where now in this case the approximating rectangle will be parallel to the axis. In the previous case with the disc method and the washer, it was perpendicular. So we're talking about how is this changing as it grows out. So that's our delta y, we have h of y and p of y. So in the shell method, to find the volume of a solid of revolution with shell method, use one of the two formulas. If it's got a horizontal axis of revolution, like this one would have, the volume is 2 pi times, and it'll go from C to D, of P of y, H of y, dy. Now I want to point out something. This is like saying 2 pi r. Think about what 2 pi r is. 2 pi r is the circumference of a circle. So essentially we're looking at the smallest circumference, then the next biggest, and the next biggest, and the next biggest, and the next biggest, kind of layered on. And like nesting dolls, and I wish I had a set of nesting dolls, but you have the smallest one, next one out, next one out, and next one out, they grow out. That's what we're talking about here with this method. Before we talked about finding the area of this one and how the area changes, the area of this outer circle, how it changes, or the ring here, as it goes in. Now we're talking about how the area grows out to get our total volume. It would be the circumference of the inner one times the height, and you can keep going on with that. So you have all these layers. So vertical axis of revolution, if V is 2 pi times the integral from A to B, P of x, H of x, D of x. And I want to point out something as well. Vertical axis of revolution, it's in terms of x. Horizontal axis of revolution, it's in terms of y. Something else to point out. So this next page is a picture from the textbook. So in this case, it's a horizontal axis of revolution. And here's the approximating rectangle. That's your delta y by whatever height this is, our h of y. And its location inside the figure is our p of y. So where is it located is what this is talking about. H of y describes the height. Delta y describes this width, which as we know, that's our dy. In the other case, a vertical axis of revolution, P of x is this distance to the rectangle. H of x is the height, delta x is the width. That becomes our dx. So that is 2 pi times P of x times H of x dx. Okay, so we're going to use this to use the shell method to set up and evaluate the integral that gives the volume of the solid generated by revolving the plane region about the y-axis. So this will have a vertical axis of revolution. So it's going to be going around like that. So we need to find our P of x. That's the distance from the axis of revolution to this. Our H of x is this. In this case, it's 1 minus x. That describes the height y. So our volume is going to be 2 pi times the integral. And x is going from 0 to 1 of P of x, H of x dx. So that's our general formula. That's going to be 2 pi times the integral from 0 to 1. Now P of x, that's just x in this case. If you're here, you're x away from the origin. If you're here, you're still x away from this 0. So the distance of this rectangle is going to just be x away. So x for the P of x times H of x is 1 minus x dx. So it's going to be 2 pi times the integral from 0 to 1 of x minus x squared dx. 2 pi times x squared over 2 minus x cubed over 3 from 0 to 1. 2 pi times, what is it, 1/2 minus 1/3 minus 0. So it's 2 pi times 1/2 minus 1/3 is going to be 1/6. 2 pi over 6 is going to be pi over 3. Okay, and that would be finding the volume. Again, our P of x is where this rectangle might lie. H of x is the height of this rectangle. Dx is your delta x. And that's it. So some people like the shell method, some people like the disk method. Usually people like one or the other, but they're both useful for different situations. Okay, next one. Use the shell method to set up and evaluate the integral that gives the volume of the solid generated by revolving the plane region about the y-axis again. So I have a vertical axis of revolution. That's y equals 1/2 x squared. That's a parabola. And y equals 0 is this line down here. X equals 6 there. So we'll have an approximating rectangle. This is the rectangle that start out here and it works its way out. So again, the inner circumference times the height all the way out. Go to red for the next part. So we're looking for our P of x. And that's just going to be x here, because it goes right up to this axis. And then we're looking at the height, h of x, and that's just going to be 1/2 x squared. So again, volume is going to be 2 pi times the integral from, in this case, 0 to 6 of P of x, H of x dx. So it's 2 pi times the integral from 0 to 6 of x times 1/2 x squared dx. Now I can pull this 1/2 out front. It's 2 pi times 1/2 integral from 0 to 6 of x cubed dx. It's pi times what? X to the 4th over 4 from 0 to 6. Pi times what? 6 to the 4th over 4 minus 0 to the 4th over 4. This comes out to be 324 pi. That'd be the volume of the shape that comes around. Okay. Kind of like a bowl with vertical sides. Okay, so we've done two of them that are vertical axis of revolution. What's this next one? Looks like it's use the shell method to set up and evaluate the integral that gives the volume of the solid generated by revolving the plane region about the x-axis. And this one's going to have a horizontal axis of revolution. So we need to come up with a formula for our h of y. So how y will dictate how wide this is, essentially. If we know y equals 2x, if y equals 2x, then y minus 2 equals negative x. Divided by negative 1, 2 minus y equals x. So our h of y will be 2 minus y. Let me back up on that. No. Okay, so h of y is going to be, we have this, in terms of this line, in terms of y solved for x is 2 minus y. But what is h of y? There's a little more to this. H of y, given our location, is 4 minus the 2 minus y. So h of y is going to be 4 minus 2 plus y, which is 2 plus y in the end. So we can determine what y is going to be, what h is going to be based on 2 plus y. So if y is 0, we're at 2. This distance is 2. If y was down here at negative 2, this distance is going to be 0. Okay, so it's 4 minus this line here. This line is described in terms of x, solving for x, in terms of y is 2 minus y. So it's 4 minus this line. That describes this distance. 4 is this side, 2 minus y is that side. That's where that comes from. Okay, now what's our p of y going to be? It's going down in the negative direction. It is touching the axis, so it's just going to be negative y. Okay, so there's a little more setup here. Our volume is, again, 2 pi times the integral, this time from 2 to 4. Nope, I take it back, I'm going vertically. From 0 to negative 2 of p of y times h of y dy. So our volume is going to be 2 pi integral from 0 to negative 2, from 0 to negative 2 of negative y times 2 plus y dy. That's negative 2y plus y squared dy. That is negative y squared plus y cubed over 3 from 0 to 2. Two pi times what? I'm supposed to go negative 2 to 0. I'm sorry. Let me fix that. Negative 2 to 0. Otherwise, I've got to put a negative out front. So it's going to be putting the 0, negative 0 squared plus 0 cubed over 3 minus the quantity, the negative of negative 2 squared plus negative 2 cubed over 3. 2 pi times what? Double negative here. Okay, so negative 2 squared is 4. Got a negative there, got a negative there, so that's a plus 4. And then negative of, this is negative 2 cubed is negative 8. So negative 8 is positive 8. Okay, I feel like I have a negative issue. Yeah, I do, because I forgot to distribute this negative. Okay, and that should be the negative. Okay, so this does come out to be a minus here. So we have 2 pi times 4, the quantity 4 minus 8 thirds, and that comes out to be 2 pi times 4 thirds, or 8 pi over 3. Okay, let me just recap that one. This height is going to be this side minus this side. That's 4. This side over here is 2 minus y. That's why it's 4 minus the quantity 2 minus y. It's 4 minus 2 plus y, or 2 plus y. It's our h of y. P of y is negative y because it's going out in the negative direction. It's negative 2 to 0 because negative 2 to 0 here. Of negative y times 2 plus y dy. Distribute that. Got to remember our negatives. And I got a negative y squared minus y cubed over 3 from negative 2 to 0. You apply your limits of integration, and you get 8 pi over 3. So let's talk about the two methods now. We've done 3 problems with the shell method, and let's compare it to the disk method. When to use which one? The disk method. Use that when the representative rectangle is perpendicular to the axis of revolution. And the shell method you use when the representative rectangle is parallel to the axis of revolution. So perpendicular versus parallel. So we're going to use the shell method to set up and evaluate the integral here. And it goes about the line y equals 4. So let's see what our figure looks like. Here's x squared. Here's 4x minus x squared. And if you want to see where they're meeting, x squared equals 4x minus x squared. 0 equals 4x minus 2x squared. So that's going to be 2x times 2 minus x. So x equals 0, x equals 2. So this is a 2 here, that's 0. Okay, and then it's going about the line y equals, or x equals 4. So first of all, let's think, what's our p of x? And let me just draw a representing rectangle. There we go. Our p of x. Now, when x is nothing, we're at 4. When x is 2, we're at 2. It's going from being a distance of 4 to 2, or 2 to 4. That's how our x is going to be, or this distance is going to vary for p of x. So p of x, it would be 4 minus x. So when x is 0, we're all the way out here. When x is 2, we're at there. How about our h of x? So h of x will be the upper curve, and the upper curve is 4x minus x squared, and the lower curve is x squared. So h of x is 4x minus x squared minus the lower curve, which is x squared. So we're looking at 4x minus 2x squared. Okay, so our volume is 2 pi times the integral from 0 to 2, because x is going from 0 to 2, of our p of x. h of x dx. So 2 pi times the integral from 0 to 2. P of x is 4 minus x. H of x is 4x minus 2x squared dx. Okay. So we FOIL this out. We're going to end up with 16x minus 8x squared minus 4x squared plus 2x cubed. So that's 16x minus 12x squared plus 2x cubed dx. So we can integrate that. That's just a polynomial. 2 pi times 8x squared minus 4x cubed plus x to the fourth over 2 from 0 to 2. Eight times 2 squared minus 4 times 2 cubed plus 2 to the fourth over 2, all minus 0. It's 32 minus 32 plus 8. Looks like it's 16 pi. Okay. So next one, we're going to make a choice. Decide whether it is more convenient to use the disk method or the shell method to find the volume of the solid of revolution. Okay, so y equals 4 minus e to the x. I did my best to draw this on the computer. So first of all, if we look at the shell method, here's our approximating rectangle, P of x, and then we have our h of x and our delta x. So our volume is going to be what? And if we want to check where is this hitting, 4 minus e to the x equals 0. 4 equals e to the x, so natural log of 4 equals x. So it's integral from 0 to natural log of 4 of our p of x. P of x is just x in this case, times our h of x, which is 4 minus e to the x dx. I forgot my 2 pi. This will be 2 pi times the integral from 0 to natural log of 4 of 4x minus x e to the x dx. So that integration, that is possible. This x e to the x is going to be a little bit tough. I mean, that's going to be, you could do integration by parts for that, or number 82 from the integration table. The integration table in the book. The other way to do this, let me draw this again. In this case, we would have this perpendicular. So remember, it's going to be v equals pi times the radius of x squared. I think this is the radius of y in this case, dy. So we have to solve this for y. We'll solve for x, excuse me. So y equals 4 minus e to the x. y minus 4 equals a negative e to the x. So 4 minus y's and 4's look alike. It's going to be e to the x. So the natural log of the absolute value of 4 minus y equals x. That would be our function here. This is what this height's going to be. This is going to be the natural log of the absolute value of 4 minus y. So our volume in this case is going to be pi times the integral from 0 to what? If x is 0, e to the 0 is 1, 4 minus 1 is 3. So 0 to 3 of the natural log of the absolute value of 4 minus y dy. I've got to square this part. Now the second one, the integration is not as pleasant. However, you could do this with number 90. The number 90 integration formula. These are all found in Appendix B in your book. I personally would prefer the shell method in this case. So, shell method, integration doesn't look as intimidating. This natural log makes it look tough, but it's still doable. It's still doable. Okay, let's go ahead and look at something else. So in example 6, we're actually going to work it out, but we get to choose which one we use for the different situation. We have y equals x squared, y equals 0, and x equals 2. It's going to go about, in the first case, the x-axis, then the y-axis, then y equals 4. X equals 4, excuse me. So here's our shape. This is 2 here. Y equals 0 is down there. So in the first case, we're going to go around the x-axis. So in that, I would draw I think it's simple enough to draw a perpendicular approximating rectangle. And the radius of that is just going to be x squared. So the volume here is going to be pi times the integral from 0 to 2 of x squared squared dx. That's pi times the integral from 0 to 2 of x to the 4th dx, which is pi times x to the 5th over 5 from 0 to 2. That's pi times 2 to the 5th over 5 minus 0 to the 5th over 5. That's going to be pi times 32 over 5. Or 32 pi over 5. So that's our first case. In our second case, we're going to go around the y-axis. So, what kind of approximating rectangle should we have in this case? We can solve for x and get a perpendicular approximating rectangle going this way. Or if we keep this in terms of x as the independent variable, then our h of x is x squared. And our p of x is just x. So in this case, our volume is going to be 2 pi times the integral, and x is going from 0 to 2 still, p of x, which is x, times h of x, which is x squared, dx. 2 pi times the integral from 0 to 2 of x cubed dx, which is 2 pi times x to the 4th over 4 from 0 to 2. That's going to be 2 pi times 2 to the 4th over 4 minus 0 to the 4th over 4. 2 to the 4th is 16 over 4 is 4. 4 times 2 pi is 8 pi. Okay, so we had a case where it was better to use the disk method and the shell method. Now in the last case, I'm going to redraw this shape so I have more space. Draw it down here. Here's our shape. Here's 2. It's going to go about the line x equals 4. So it's going to go around this. So what would be better if we did a perpendicular approximating rectangle or a vertical one? If we did perpendicular, we have to solve for x, or solve for x. It'll be square root of y. So this side's square root of y. This side's going to be 2. So it would be like square root of y minus 2. And then we have to square that. So integrating that's going to be a little messy. What if we did it the other way? If we did a vertical one again, the hardest part is to come up with our p of x. The h of x is just going to be x squared. So p of x, the full distance is 4, and we're losing some as we get to this point, so minus x. So for part C, I'm again going to use the shell method. And that's going to be volume is 2 pi times the integral from 0 to 2. P of x, which is 4 minus x, times h of x, which is x squared, dx. So it's 2 pi times integral from 0 to 2 of 4x squared minus x cubed dx. That's going to be 2 pi times 4x cubed over 3 minus x to the 4th over 4 from 0 to 2. So 2 pi times 4 times 2 cubed over 3 minus 2 to the 4th over 4 minus 0. That's going to give us 40 pi over 3. Okay. That's our last one. So this is going around this shape. You're going to get this over here. Some of those fun shapes you get to draw in your CAD class if you're an engineering student. Okay. We're going to the last example from this section. Use a graphing utility, I guess I'll see it there, to graph the plane region bounded by the graphs of the equation. Use the integration capability of your calculator to approximate the volume of the solid generated by revolving the region about the y-axis. Okay, and it's x to the 4/3 plus y to the 4/3 equals 1. X equals 0, y equals 0 in its first quadrant. Okay, the harder part's actually putting this in terms of y. Subtract x to the 4/3 from both sides. Y to the 4/3 equals 1 minus x to the 4/3. Y equals 1 minus x to the 4/3 to the 3/4. So if you graph that in the first quadrant, you'd see something like this. So being that it's like this shape is going around the y-axis, I think it would be best to use the shell method, because then we'd have a vertical rectangle. We already solved for y, so our h of x is going to be 1 minus x to the 4/3 all to the 3/4. This is one up here, one down here. Our p of x is just x. So the volume is going to be 2 pi integral from 0 to 1 of x times the quantity 1 minus x to the 4/3 to the 3/4 dx. So I put this in my calculator, and you can too, and I've shown you how to do that. And you're going to have approximately 1.5056. Okay. In the calculator, this is how I had to make it look. Remember using the F3 for integration. And it gives you the integral with a parenthesis, and I did x times parenthesis 1 minus x with a caret on this part of parenthesis 4/3. If you don't do the parentheses, it raises it to the 4th power and divides the x by 3. And then you need to close that parenthesis and then raise it to the 3/4 in parentheses, comma x, comma 0, comma 1. Okay. So you can put that in your calculator. Okay, and that's the end of this section. So I know we learned 2 methods. They can be a little confusing which ones to use, but try to use the one that's going to make life easier for you. That's what it's all about here. And you're going to derive the answer with less error. Okay, so I'll see you later. Thank you.